um, as far as my own work is concerned, it has been done together mainly with my student Heike Eisenlohr and Sang-Sub Lee, a postdoc from Munich, who helped a lot with numerics. So here is what I want to cover in this talk. I will start out with a quick reminder on aspects of quantum criticality as far as they are relevant for this talk. Then I will briefly walk you through a few basics of the Hubbard model and the Mott transition to be expected there, and a few of the early thoughts and concepts which have been developed. Then I will focus on a particular puzzle which emerged in numerical studies of the Hubbard model. Namely, there is a kind of quantum criticality seen in the resistivity at elevated temperatures. First in studies of dynamical mean field theory of the Hubbard model, and then also in experiments. And this has been a puzzle, and I will explain you why. And then I will tell you about our own investigations, which essentially were geared at understanding the puzzle. And I will show that in dynamical mean field theory, there is a very special type of local quantum criticality occurring in the vicinity of the Mott transition. And at the end, I will discuss some broader implications, including the physics of bad metals, in particular also doped Mott insulators. So quantum criticality starts, of course, with the question, what's a phase transition? You all know what a phase transition is. That's this one. It's a change of collective properties of a macroscopic number of particles. A quantum phase transition is the same thing happening at t equals 0, which then apparently, in contrast to what you saw on the previous slide, must be driven by quantum fluctuations. There are various views on quantum phase transitions. One is that there is a change of the nature of entanglement in the ground state of the system. Now, this is the by now famous and time-honored phase diagram, generic phase diagram for a quantum phase transition, where you have a non-thermal control parameter here called R on one axis, temperature on the other axis. There is a zero temperature phase transition between an ordered and a disordered phase. And if it's continuous, you would call this here a quantum critical point. And then there is a quantum critical region on top of this quantum critical point. And here in this example, there is an ordered phase which breaks the symmetry, and this is bounded by a finite temperature phase transition. For the Mott transition, I will be discussing in this talk. This is actually not the case. And apparently, my screen sharing has broken. Let me just get it back. It takes a second. Here we go. Hope that you can now see it again. Yes, looks good. So again, that's a generic quantum critical phase diagram. And of course, this physics has been observed in many, many compounds. For instance, in the context of magnetic quantum phase transitions, and one of the famous and well-studied examples is thallium copper chloride, which you can drive through such a magnetic order-disorder phase transition by varying pressure. Now, if we want to study quantum criticality theoretically, then one of the successful analytical approaches is to identify an order parameter and then write down an order parameter field theory and analyze this order parameter field theory. And then it turns out that the quantum critical properties are controlled by a critical fixed point of the renormalization group flow of this field theory. In many cases, the underlying field theory is known, and I'm emphasizing this because I will be talking about an example where we don't know the critical field theory. But here, for the example which I was showing the previous slide, a magnetic order-disorder transition, here it's pretty simple. We have an antiferronetic state on one side of the phase transition. So if we can write down an antiferronetic order parameter, which is called phi here, and then we have a standard phi-4 type theory, which is written here in the box, which describes the space and time dynamics of this order parameter. And this can be analyzed, for instance, by renormalization group techniques, and fully describes the critical properties of the system. Now, such a theory, I should emphasize this here, is, as you can see, it contains space gradients and it contains time gradients. So space and time both enter, so we have fluctuations in space and time. And Usually that means that both the correlation length in space and the correlation time diverge upon approaching a critical point. So these two things, psi tau is the correlation time, psi is the correlation length, are then related by the relation which I've written down here, where z is a dynamic critical exponent, which again describes how space and time enter. Z equals 1 would mean space and time enter symmetrically. And then this is, for instance, a requirement to have a Lorentz invariant theory. Now, in various places of the quantum critical literature, so-called local quantum criticality has appeared, which refers to situations where there is no standard spatial criticality in the sense which I've just discussed. There are various instances of this. One where the situation is obvious is quantum criticality in quantum impurity models. This refers to situations where you have a small number, so a finite number of degrees of freedom, for instance, a single impurity, like a Kondo spin, coupled to a thermodynamically large bath, and there is a phase transition where only the impurity degree of freedom becomes critical. Then that's essentially a zero-dimensional problem concerning criticality. There is still the possibility to have non-trivial critical behavior because there's an infinitely large path. But in this situation, you would expect that there is well-defined criticality in time. So on the time axis, there's typically a divergent correlation time, but there is no non-trivial criticality in space, essentially because, again, there is only a finite number of degrees of freedom which get critical. There are other instances of local quantum criticality, and one which has become reasonably famous is local quantum criticality, which has been discussed in heavy fermion systems, which is thought to arise from the breakdown of the Kondo effect. You know, the Kondo effect is something where local magnetic moments get screened by a metallic bath. That's in some sense a lattice generalization of the single impurity Kondo effect. And it has been proposed, and this goes back to work of Ximiao C and collaborators, that the breakdown of the Kondo effect can lead to a type of criticality which is local in space in the sense that it's not accompanied by non-trivial spatial criticality. This has been formalized in so-called extended dynamical mean field theory. In particular, this started in this 2001 paper, which is cited here. And there have been a number of experiments which have argued that such criticality is realized in actual heavy fermion compounds. Beyond that, there are a number of systems which have been studied theoretically where it has been shown that the dynamic exponent is formally infinity. One is a dissipative XY model in 2 dimensions studied by Varma in 2015, and there are a number of other examples. There is still a spatially diverging correlation length, but it diverges much slower than the correlation time. Again, Z formally infinity. And this has also been termed local quantum criticality. So the main purpose of showing this slide here is that local quantum criticality has appeared in various contexts, and it doesn't always mean the same thing. But most often means, again, that there is no non-trivial criticality in space, but only one in time. Let me just make one remark here, namely, if one thinks about, and I have the feeling that my screen sharing again is broken. I'm sorry for that. So we tried this before, but apparently there is a, things are not really stable. Let me just, restore this. So I would just like to draw your attention to the red remark here at the bottom. Namely, if one thinks about the breakdown of the Kondo effect, then again, within a dynamical mean field theory description, and you will see what this means on a technical level in a second, it is a local phenomenon. But however, if you go beyond extended dynamical mean field theory, the Kondo breakdown is not a purely local phenomenon. This casts some doubt on the interpretation of the corresponding experiments, but this is not the main topic of this talk. Okay, what I will now focus on in the following is the Hubbard model and the Mott transition. So first of all, what is a Mott insulator? A Mott insulator is a occurs in a system of interacting particles, in particular interacting fermions, well, it also exists for bosons, which move on a lattice subject to a strong local repulsion. And if you make this repulsion much larger than the kinetic energy, and if you are at a filling condition which says they have one particle per site for fermions, then the particles get localized due to interactions, and that's a Mott insulator. And this is schematically shown in this picture down here, where you see that in this particular potential, essentially one particle is occupying each of the sites. So this Mott insulator has a gap to charge excitation, so it's an incompressible state. It has no Fermi surface because it's insulating, but for fermions, it has residual degrees of freedom. Therefore, there is non-trivial magnetism because every particle on each side can still have spin up or spin down. Now, the focus of this talk will be on the bandwidth-controlled Mott transition. So we will stay at half filling and we will vary the interaction strength. And then for this transition, one can ask a number of questions, in particular in the light of what I told you before about quantum phase transitions. First of all, the conductivity of a system, be it formally a metal or an insulator, is always finite at t equals 0, because also an insulator has thermal excitations across the gap at finite temperature, which means the transition is only a well-defined transition at t equals 0, because only then you can distinguish infinite and zero conductivity. And then the question is, what happens at finite temperatures? Natural question is, if you come from a metal, what is the fate of the Fermi surface at the transition? What happens to the metallic low-energy quasi-particles when you go across the transition? Is magnetism a relevant player for understanding the transition? And again, since magnetism is important, one has to realize that there are many situations where the insulating state emerges together with magnetic order. And then often the transition can be understood in terms of a band transition, because band splitting arises from magnetic order. But if you are interested in Mott phenomena, so genuine strong correlation phenomena, then you can ask the question, does genuine Mott quantum criticality exist? Which means Mott quantum criticality in the absence of the onset of magnetic order. And so the purest form you can imagine then would be the transition from a metallic, from a liquid-like state, into an insulating state which does not have magnetic order, and so, for instance, could be a topological spin liquid. This is a question which has been discussed in a number of papers, and the list which I cite here is definitely incomplete. And the typical approach is actually to look at low energy effective theories which incorporate the spin liquidity and then try to construct something which enables a transition into a metallic state. So there is genuine low temperature physics, this is, I guess, in general, a problem which is not fully understood. A number of theoretical proposals do exist, based essentially on parton constructions which start from mean field theory plus fluctuations, but a complete picture has not emerged. Now, if you look at experiments, then of course you have to face a number of complications, and what I'm showing you here are old experimental data for the compound vanadium oxide. And what you see is a phase diagram, temperature versus pressure. And what you can see is there is an antiferritic insulator at low temperatures, which is bounded by a line of finite temperature phase transition, which mark the onset of magnetic order. But there is also a line of first order transitions here at finite temperatures, which ends in a critical endpoint. And this is now, which means crossing this line here is a insulator to metal or metal to insulator transition. Again, it's a first order transition. And this ends at this critical endpoint, which means you can connect this metal and this insulator by moving along a path like this, which of course is in line with what I said before, namely metal and insulator cannot be sharply distinguished at finite temperatures. Okay, which means there is this complication of magnetism at low temperatures, but despite this, there is still the possibility to have a, if you wish, pure metal to insulator transition at finite temperatures in this form. Now, there are a number of other experiments on other compounds which show similar phenomenology, and a number of them come from organic compounds. which have the advantage that they can very easily tuned by pressure, because these are typically soft materials. What you see here is, again, a temperature pressure phase diagram on this particular compound, this ET salt, which is written on top. And you see a metal, a Fermi liquid metal on the right-hand side, and you see insulators on the left-hand side. At low temperatures, there's magnetic order, but above this ordering transition, which is here, there again is a Mott insulator, which is separated from the metal by a first order transition line, which is this one here. And there is a critical endpoint. Okay. And here are other organic compounds with very similar phenomenology, temperature pressure phase diagrams of the same type, metal on the right-hand side, insulator on the left-hand side. And the difference here is that the insulator in the left graph is a valence bond solid. So it's a state which is not magnetically ordered, but instead breaks lattice translation symmetry via dimer formation, so spin singlet pairing. And the picture on the right-hand side shows a material which is believed to be a genuine spin liquid. So no magnetic order, no symmetry breaking down to the lowest measured temperatures. The interesting thing here is that in both cases, there is a superconducting phase sandwiched between the low temperature magnetically ordered state and the, and I apologize again for this interruption, but we are back here. Superconductor sandwiched between the Mott insulating state and the metal. Okay, now let's get into theory. The standard description is the Hubbard model, and in this talk I will be exclusively focusing on the one-band Hubbard model as written here. So we have a kinetic energy in the first term that describes hopping of particles on the lattice as shown in the left picture, and we have a we have a local repulsion. So the Coulomb interaction between the electrons has been stripped down to the local on-site term, and that penalizes double occupancies on the lattice, as shown in the right-hand picture. So we take this model, we stay at half filling, so we have on average one particle per site, and we vary the ratio of T over U. So we are at half filling. So at U equals 0, you can now think about, so this quick discussion which comes now is discussing a single particle spectrum. I will be focusing on the momentum integrated single particle spectrum, the momentum integrated single particle spectral function and the imaginary part thereof. So at U equals 0, what you see is just the density of states of your conduction band. That's a featureless curve, which produces something which is finite at the Fermi level. And if you go to the opposite limit of U large, then, which essentially you can understand by starting from the atomic limit where you only have U and no kinetic energy, then the single particle spectrum consists of two peaks, which are located at plus, at minus U over 2. And these are called Hubbard bands. And again, this formula shows you what happens in the atomic limit where kinetic energy is 0. That's an exactly solvable problem. And so what you see are two Hubbard bands, and they are separated by a gap, the so-called Mott gap, whose magnitude is essentially U. Okay. Now we want to go from the upper situation to the lower situation, and there will be a transition. And the question is, what happens there? And there are obvious things that you could think of. You can think of the quasi-particle weight, so the weight of the Fermi liquid quasi-particles, which may go to 0 at the transition. This can be accompanied by divergence of the effective mass of these quasi-particles, and you would expect that the Mott gap, in some sense, if you come from the insulating side, it goes to 0 upon approaching the transition. Now, this is an unsolvable problem, but progress has been made using dynamical mean field theory. So let me briefly describe you what this is. Dynamical mean field theory starts from the assumption that correlation effects are local in space, which means for the complicated lattice problem, which has a single particle self-energy, which depends on momentum and frequency, we approximate this as being momentum independent. This is an approximation which one can show becomes exact in the limit of infinite dimensions, but this is of not much relevance for what I will be discussing here. So let's just take this as an approximation for an actual lattice model in finite dimensions. If we make this assumption, then it turns out that the problem can be formulated as a mean field theory. So it takes the form of a local correlation problem, namely an Anderson impurity model, supplemented by a self-consistency condition. So this is written down in equations on the next slide, which again you can't see because my screen sharing has again broken down. I apologize for that. But we can certainly rectify this. And here we go. So what you see here are the formalities of the dynamic field theory for the one-band Hubbard model. And the experts in the audience know these equations, and I will not explain them in great detail. The main thing is that the problem which one has to solve in practice is this problem here, which constitutes a quantum impurity problem, a so-called Anderson impurity model it describes a single level coupled to a fermionic bath subject to a Coulomb or Hubbard-like repulsion, U. And so this is something which can be solved on the computer, and this must be supplemented by a self-consistency condition as in any mean field theory. And the self-consistency condition can be, for instance, written like this, which relates the lattice Green's function to the Green's function of the impurity problem, or relates the lattice self-energy to the self-energy of the impurity problem. So what this means in practice is that as in any mean field theory, one has an iterative scheme, which is schematically shown here. One starts with the Green's function, which one uses to calculate the self-energy, then puts this into an impurity problem, solves this, gets back a self-energy in the Green's function, and iterates this scheme. And the four gentlemen you see here have been heavily involved in developing this in the 90s. And by now, this is the established method to solve strongly correlated problems, again, under the approximation that the self-energy is local. There are extensions of DMFT to, for instance, clusters, but this is something which I will only mention towards the end. Okay, now if you apply this type of theory to the Mott transition, again, on the single band Hubbard model, then this graph here shows you schematically what you get. So what you see here is now the phase diagram of for the Hubbard model obtained in DMFT. And you have temperature on the vertical axis and U over T, so the ratio between the interaction strength and the kinetic energy on the horizontal axis. There is a first order line of transitions between a metal and an insulator, which terminates in a critical endpoint. And this line is surrounded by a regime of coexistence as you would expect for a first order transition. So if you look at the single particle spectra, which come out from DMFT, then on the insulating side, you get a picture which is shown here. So as expected, you get two Hubbard bands. They are separated by a gap. You get the insulating state. And on the metallic side, but already at sizable correlations, you get a picture as shown here on the left-hand side, which shows two Hubbard bands, but there is in the middle a so-called quasi-particle peak at the Fermi level, which characterizes the metallic state. So one can actually understand this structure here by saying that at high energies, there are local moments forming, and this is what characterizes the presence of these Hubbard bands. This is formation of local moments. And then these local moments essentially get self-consistently screened, and this is in some sense a DMFT version of the Kondo effect. And this is what produces this metallic peak at very low energies, and then essentially eats up the magnetic degrees of freedom and makes this a Fermi liquid metal. Okay, this is what comes out in DMFT. So this looks nice. One has to be aware of the fact that, and again, you can't see my next slide. Now things are broken. Michelle, I'm wondering whether I should switch to the other computer here. I'm a bit pissed off these problems. am I a co-host also for
you
my...
You're a co-host on the iPad. I can make you a co-host on the...
If you make me a co-host on the other computer, that's probably more reliable. I'm sorry for that.
Okay, you should be now.
I was hoping that this works, but didn't. So let me just see. So working on it. So, can you see something?
Yes.
Okay, I'm sorry. This was unexpected complication, but I hope that we can continue like this. Okay. Can't use my pen anymore. Good. So here we are. And this is where I was. Now, the caution here is that the dynamical mean field theory, because it's a local approximation, it neglects momentum dependence. It is missing magnetism, collective magnetism, in the sense that spin correlations between neighboring sites are missing. That means that the insulator, which you see here on the right-hand side of the phase diagram, has essentially free spins. There is no magnetism, not even magnetic correlations, which means there's a residual entropy of log 2 per site. Of course, a real Mott insulator will have magnetic order or some spin liquid behavior at low temperatures, which is missing in DMFT, which automatically means that DMFT, if it's valid at all for a real system, can only be valid at elevated temperatures. Okay. Now, the conclusion from this, if you're conservative, would be that the phase diagram in reality could perhaps look something like that. Again, the same axis, temperature on the vertical axis and the correlation strength on the horizontal axis. You have this line of first order transitions, which ends at the critical endpoint. But at low temperatures, you have the onset of magnetic order, which again is not described by DMFT. But if you are lucky, this line of first order transition sticks out of this magnetically ordered phase, and then the metal-to-insulator transition, as described by DMFT, is still part of the real physical phase diagram. And as you saw from the experimental examples which I showed you, this in fact seems to be realized in a number of compounds. Okay, so in this sense, you would hope that DMFT has a reasonable description of the physics above the magnetically ordered phase. And for this to be true, of course, you have to make sure that magnetic order is not so strong that the corresponding critical temperature goes above the temperature of the critical endpoint. And that means this DMFT in particular has a chance to be valid if the system is frustrated such the magnetic order is suppressed. Okay, now, this was the state of affairs like 10 years back. And so everybody had accepted that DMFT describes what it does and it has the shortcomings which it has. That's about it.
Matthias?
Okay, yes.
Matthias, sorry, before you move on to the next section, there was a question from Bruce Golay.
Yes, please.
Yes, Matthias, I was just wondering, both parts of the red phase in this diagram are magnetically ordered or spin liquid or have magnetic properties, but they would be different magnetic properties on either side of the first order transition. Is that correct or not?
Well, okay, there are now various possibilities. One is actually that the magnetically ordered phase is just one magnetically ordered phase, and that there is only a line sticking out of this phase, and there is no actual transition in this ordered phase. So if you recall the phase diagram of vanadium oxide, I just jump back to this, then this is precisely what happens. So for instance, this one here, then you see there is one magnetically ordered phase, not two. It's an insulating phase. But then there is this line sticking out, and that is, again, the line which presumably is described by DMFT. So if you were now to suppress magnetic order completely by something, by some miraculous knob to tune, then you could imagine that you can suppress this magnetic order down to 0 temperature, and then you would be left with this first order line sticking out, ending in a critical endpoint. In principle, there is the possibility to have further transitions inside the ordered phase, that you have 2 different ordered phases, for instance. In principle, you could also have an ordered metal and an ordered insulator separated by a band insulator type transition, but then things would get more complicated. So there are a number of possibilities. The key point I'd want to make here is just that, again, all this type of magnetic order is not described by DMFT, but DMFT has a chance to be correct above the corresponding ordering temperature.
Okay, thank you.
Okay, let's get back here.
Matthias, if I can also jump in and
sure.
Going back to Bruce's question. So in the example for vanadium oxide, where this line comes out of the ordered phase, is the idea that it actually, there's a ghost of that line that would be within the magnetically ordered phase, or it just really, in the real material, or it just pops out straight from the phase boundary? Because in that figure you're showing right now, there's a line that is underneath. So I guess I want to ask if there's only one phase, is there a remnant of that ghost line, which is some kind of crossover? I guess my question is the line that you have.
Your question is perfectly well taken, and I must admit you're just uncovering my ignorance here. So I'm not sure. Can you actually see my mouse pointer?
Yes.
So what I'm just wondering myself, and this is in some sense where your question is hitting, if this transition here is first order, this line of transitions is first order, then it would mean there is a jump if you go from here where my mouse pointer is now to this point, right?
Mm-hmm.
And if there is a jump here, then, and if all these transitions are continuous, then this is thermodynamically inconsistent, right? Because mm-hmm. there's a jump here and this jump must continue.
Right.
And of course, for the vanadium oxide, there must be an answer, which unfortunately I don't know. I'm not sure whether anybody in the audience, André-Marie, might perhaps know it.
In cluster calculations, one can see sort of a shadow of this transition if one looks at the condensation energy. In other words, why is it becoming antiferromagnetic? Why is it not paramagnetic? So if you look at this condensation energy defined that way, which is a little bit artificial in some ways, because this normal state is not the stable state, then you find that on one side it's controlled by
so you're saying there is still something here?
I'm saying that there's a crossover.
Okay.
Below, all the way to 0 temperature. If I ask the question, what is the condensation energy? What is the difference between the energy of the ordered state and the not ordered state? What you see that one side, it becomes antiferromagnetic because of potential energy, and on the other side, because of kinetic energy. So that's a crossover from that point of view. But yes, it's just one phase once you go in the thermodynamically stable phase. Another way to say it is that on one side, it would be more like Slater physics, and on the other side would be more like Mott physics, or maybe Heisenberg, I should say, Heisenberg physics. In one case, on one side, it's nesting that controls, and on the other side, it's a Heisenberg exchange, and the crossover between the two is continuous. And yes. it's this Mott transition, this sort of Mott transition that you don't see anymore. That is you can look at it as the cause of this crossover. But yeah, let's not spend too much time on this. I guess I want to.
Yeah, I guess that's not the key thing. Again, for the vanadium oxide, there must be a clear-cut experimental answer, but these data, which I'm showing here, are from the 70s. So I'm not sure whether this has been investigated in any detail at this point. in these phase diagrams here, you actually see that the antiferrometric phase is always on the left-hand side of this first order line, and therefore the question doesn't appear in the same way. Same here. Okay. I have this strange thing which says I should remove this window. I'm not sure what this actually means. Perhaps I just continue. I think it doesn't disturb the presentation much. Okay, good. Let's get back here. So, puzzle, new section, puzzle. The puzzle is that, oh, I see that you cannot. Can you actually see my current slide? Now you can see it. Very good. Okay. So the puzzle is that in numerics, signs of quantum criticality have been seen. So what this means is, and I'm now reporting here results from this paper of Vlad Opozavljevic and co-workers from 2011, is that what you see here is again the phase diagram from DMFT, is that in this regime, which is color shaded here, this yellowish orange thing, the electrical resistivity as calculated from DMFT has shown signatures of quantum criticality. And again, here we are above this critical endpoint. You see the critical endpoint is down here where my mouse pointer is. And again, we're now talking about this regime up here. So what has been seen? This is shown here on this slide. The resistivity has been calculated again within DMFT, and the resistivity is now here shown along a number of trajectories in the left-hand plot as function of temperature. And these are trajectories which actually run in parallel to the red dashed line, which is labeled instability trajectory in the phase diagram, which you see on the upper right. And again, that is the resistivity. And if these data here, and you see trajectories actually which look metallic, which are on the left-hand side of the red line, which go down to the metallic Fermi liquid. These are the resistivity trajectories down here, the lower part of the phase diagram. And you see others which are insulating, which are on the right-hand side of the instability trajectory. And then you can do a scaling procedure, which leads to a collapse of the data as shown here in the center plot. And this collapse of the data is now a collapse of data where you take temperature, you take the absolute temperature over some reference temperature and the resistivity relative to the resistivity on the red line. And this is a scaling collapse, which is characteristic of a quantum phase transition, because again, it's scaling where the absolute temperature enters. So this is clearly an indication, or let's say, this is conventionally taken as an indication for quantum criticality. Now, at the point when this paper appeared, people thought, oh, that's perhaps an artifact of DMFT. So not many people took it really seriously. But then the group of Kanoda actually tried to verify this prediction experimentally on a number of organic compounds, which are listed here on this slide. And again, these are all tunable by pressure. And you see resistivity curves as function of pressure, and you can plot them in this phase diagram, and you can do the same scaling procedure, and you get a beautiful data collapse. I now spare the details because I feel I will be running out of time. So this, in some sense, says that the same thing which has been found in DMFT is also present in the experiment, which I guess was an even bigger surprise. So that raises now the questions. Here we have, and that actually applies both to DMFT and to the experiment, we have a first order quantum phase transition. Why is there quantum critical scaling? The scaling would only be expected for a continuous phase transition where you would see true quantum critical phenomena. That then raises the question, is there somewhere a Mott quantum critical point? Again, not in the phase diagram which we have just looked at. Is it hidden somewhere? And can we understand this if there is a Mott quantum critical point? Is there a critical field theory? And then, of course, is the agreement between DMFT and the experiment just accidental, or is there something deep behind it? And does it have some broader implications? And I will now quickly walk you through our detailed studies of this problem. So we essentially thought about these puzzles and then found it worth revisiting the numerics, which I just showed you, with larger accuracy. And we first asked the question, is it possible for DMFT to produce something quantum critical at all? And that's a question which in principle has a yes/no answer. And interestingly, the answer is yes. And I will just briefly explain this to you. So since we are talking about DMFT, we talk about something which has criticality only along the time or the frequency axis, not along the space direction, again, because there is no non-trivial spatial physics in DMFT. So what we would be looking for is frequency power laws in the spectral function. Now, this is the phase diagram which I showed you before, and you've seen the two spectral functions here. And there is no possibility for a frequency power law. But if you now imagine you start from the insulator and move towards the point where the Mott gap closes. So you start from the spectral function on the right-hand side and make U smaller, which means the two Hubbard bands approach each other. Then at the point where they touch, which is now shown by the red spectral function in the middle, this is where essentially the insulator ceases to exist. And this is the point where there is room for a power law in the spectral function at zero frequency. Zero frequency is now here in the middle of this plot. That is actually the only possibility in this DMFT for the single band Hubbard model to produce a frequency power law. So this then would occur in the insulator at the point where the Mott gap closes. The interesting thing is if it occurs, then it is in the insulator in the regime where it is only metastable, because this is on the left-hand side of the coexistence line in the phase diagram. And in this regime, actually, the metal is a thermodynamically stable phase, but the metal cannot develop a power law. It cannot become critical, but the insulator can. And then the question is this consideration of any relevance? Again, that's just what I said. The metastable insulator in this limit, where U goes to UC1, UC1 is this left coexistence line, can develop frequency power laws. This can be a quantum critical state. Now, if this actually happens, then the spectral function again would have a power law. And from this power law, and I've now just assumed an exponent R here for this spectral function as function of frequency, one can immediately deduce that the resistivity would diverge as t to the minus 2R, because in DMFT there are no vertex corrections. So this would be an insulating state with divergent resistivity, if you cool it down. And by understanding the working principles of DMFT, one can draw a number of conclusions, namely that the relevant impurity model is a so-called pseudo-Gap-Anderson model, which has been studied in great detail, which must be in its unscreened phase. And so here in this situation, that's a remark for the experts, the impurity itself is not critical, but the criticality would be generated by self-consistency condition. Okay, so that's a hypothesis. And now we test it numerically whether this works. And I just have one further remark here, because this has been raised in other corners of studies of the metal insulator transition. A quantum critical metal actually cannot exist in DMFT, and I can argue why this is so. So I will now quickly flash a few numerical results which essentially underline the hypothesis or verify the hypothesis which I was just presenting. So what you see here are now high accuracy numerical results from simulations of the of the Hubbard model in DMFT using the numerical renormalization group as a impurity solver. What you see here is the spectral function as function of frequency on the log-log scale, and the curves approach, they are in the insulator and they approach the Mott transition from red to blue. And what you can see is that the curves upon lowering U seem to approach this quantum critical power law, which is shown here as a dashed line. They don't fully approach it because we are not able to get very close to the end of the coexistence regime because of numerical stability reasons. But this is promising. And the right-hand plot here shows the effective exponent of this spectral function, color-coded, as function of U and frequency on the vertical axis. And red means we have essentially this power law, which actually has an exponent which is around 0.8, which means there's a sizable range of U and frequency values where this power law seems to be realized. One can then, if one goes away from this point where the gap closes, one can analyze how the gap opens. This here is actually the gap as function of U minus UC1. Again, on a log-log scale, this shows a beautiful power law with, again, some exponent that is consistent with the notion of Mott criticality. Again, all obtained within DMFT. One can look for the scaling of the single particle spectral function. And I feel that I should speed up, so I will just essentially only gloss over this. The scaling, there's approximate scaling, which is seen. There is no scaling here at the high energy side because this is outside the universal regime. There's no good scaling at the low energy side, and this is something which actually we can understand, and I will just jump over this. And you can ask me afterwards if you're interested in that. So that was zero temperature. So we have a regime of power laws at the point where this is expected. And then we can follow these power laws to finite temperatures. And so we simulate the same problem at finite temperatures. And what you see now is a temperature here below the temperature of the critical endpoint. And you still see these very nice power laws. Again, that spectral function is function of frequency, log-log plot. Here you see power laws, and these curves which look strongly different are actually the ones in the metal. Recall there is a first order transition at low U towards an entirely different state. And you can heat this up further, and then you get curves like this, and they all, and again, these are now the color plots the same way, frequency and U and the effective exponent colored, and they all show a very nice power law regime, which of course gets somewhat narrower if you heat the system up, but there is a power law in this spectral function. So this is precisely what you would expect in a quantum critical scenario. And at low frequencies, the power law is smeared by temperature. That's also very natural. Okay. So this allows us to draw this phase diagram here, which essentially shows now, it's again the phase diagram of the Hubbard model, temperature versus U. And what is color coded is now the spectral function at a frequency which is twice the temperature, so where it's little influenced by temperature. And again, what is color coded is the effective exponent. And you see now, and that's the suggestive thing of this plot, you see this red regime, which shows where this power law in the phase diagram, this spectral power law does exist. And you see the typical quantum critical fan, and it's bounded by a regime of metallic states in blue and by something insulating in yellow. And there is this power law stuff in the middle. And this originates, and you can see this very nicely at this point down here, which is this point where the metastable insulator starts at t equals 0. So this has nothing to do with the physics of this critical endpoint. It has nothing to do with this first order transition line, but again, emerges from this point down there. And this is something which has escaped attention so far, because in this regime of the phase diagram, the thermodynamically stable phase is the metal. And so people did not pay much attention to the insulator. Okay, so this is, again, if you want to call this, this is Mott quantum criticality. And then with our accurate numerics, we also looked at the resistivity, and I will just flash this. We find a divergent resistivity at the transition, and we find nice resistivity scaling in our data, very similar to what I showed you before. Okay. Now, what did we achieve? Let me just summarize the numerics here. We have seen that the dynamical mean field theory solution of the one-band Hubbard model actually has something which can be called quantum critical, namely this metastable insulator, which in fact produces a scale-invariant spectrum and is responsible for this scaling of the resistivity, which means we have been able, at least on an operative level, to explain where this resistivity scaling comes from. Now, this of course raises a number of questions of rather fundamental type. And so let me just discuss this. First of all, what we have here, so the regime where this critical scaling appears is fully incoherent. So if you look at the spectral functions I've just showed you, there's no quasi-particle whatsoever. So this regime is dominated by strongly incoherent or by strongly inelastic scattering. And so we have a universally incoherent regime at intermediate temperatures. This is where this quantum critical scaling appears. And apparently, as described by DMFT, the correlation effects are fully local. Now, if you would go beyond DMFT, then non-local effects would, of course, become important at low temperatures. But it's plausible if this happens only at temperatures below the temperature of the critical endpoint, Tc, then this quantum critical scaling, which again is mainly observed up here, is not influenced. So this, as I said before, applies to frustrated systems. And this, in a sense, explains why DMFT and the experiment seem to agree so nicely. We are in this regime up here where correlation effects are local. And therefore, apparently, DMFT delivers a relatively good description of what happens experimentally. Now, on a broader scale, you can ask, is this also interesting away from half-filling? Recall what I discussed so far was the bandwidth-driven Mott transition at half-filling. And we, of course, know that a very interesting set of questions, in particular, those of cuprate superconductors, exists away from half-filling. The group of Dr. Zavljevic published a paper in 2015, which actually found a somewhat different, but in principle, similar scaling of the resistivity. And I will discuss this considering the question of, can we find bad metal regimes? You know, bad metals are discussed all over the place in many correlated electron compounds. And the question is that what we have identified here, does it have anything to do with bad metals? First, I want to remind you, at half-filling, we play the game starting from the insulator, which gets critical, and the resistivity at the critical point, which means resistivity along a trajectory here, actually diverges upon cooling, which means what at half-filling, what we have is definitely a critical insulator, not a bad metal or a critical metal. However, if you go away from half-filling, then the numerics, which I just mentioned, seems to indicate that things get different. And what I show you here are just two graphs taken from this paper, which I cited here as a first reference on this slide. And they show a temperature doping phase diagram, again, obtained from DMFT, now in the Hubbard model away from half-filling. And the green regime is one which has been called bad metal here. And you see this on the right-hand graph, which shows the resistivity as function of temperature for different doping levels. And in this green regime, which exists here at elevated temperatures, you see that the resistivity varies approximately linear with temperature, plus some offset, which is one of the hallmarks of the bad metal regime. And this happens in this regime here, which in this paper has been attributed to quantum critical behavior. And this orange line here is labeled quantum Widom line. This is a concept which appeared earlier in other papers, which essentially assign an instability line to a first order transition. And the Widom line continues this first order transition into the region of the phase diagram where there is only a crossover. Again, this bad metal regime is in a regime where there are no well-defined quasi-particles. You see this line down here, which is called resilient quasi-particles. This is where we can still identify signatures of quasi-particle physics in spectral functions. And the bad metal regime is elsewhere. So this is, again, incoherent physics. Good. I now come to my final concluding slide. In terms of outlook, so what I try to argue is that there is an interesting and, in some sense, novel instance of local quantum criticality here in this one-band Hubbard model, which we, in some operational sense, have understood in numerical studies, but for which analytical theory is lacking. And I have nothing to offer at this point. We banged our head on this, but it couldn't make much progress, simply because again, in the absence of quasi-particles with fully incoherent spectral functions, developing analytical theories is difficult. A question in this context is the fact that there is no quantum critical point in this phase diagram of any relevance. Again, I argued that this criticality emerges from the endpoint of a coexistence region, not from a true quantum critical point. But I don't know whether this is a fact of fundamental importance. And of course, for those which are interested in cuprate physics, the big question is, does any of what I told you have to do with the generic cuprate phase diagram, which you can see down here on the right-hand side, which has an interesting strange metal regime above a presumed quantum critical point, which exists somewhere at finite doping on this axis. Of course, the main difference here is that the right phase diagram is in a real two-dimensional material, whereas the left phase diagram comes from dynamical mean field theory, which is a strong approximation. But there is hope actually to link the two, and this is my closing sentence, because extensions of DMFT, cluster DMFT, have shown that this so-called Wiedom line, which is here in the phase diagram, the DMFT phase diagram, the orange one, this actually moves to finite doping and also changes its location in the phase diagram. Again, that's the same phase diagram here, but now studied with cluster DMFT. And there is hope that this can be related to the pseudo gap. And then with this, one can have a deeper understanding of the strange metal regime of the cuprates. However, at this point, this is a speculation, and a deeper understanding of what happens there is lacking. Thank you for your attention.
Thank you very much, Matthias. That was very interesting. So, so we can maybe take some questions now, if that's okay?
Sure.
Yeah, so if you can raise your hand or your e-hand, then I can let you, give you the access. So André-Marie, you had a question or?
No, not now, no. Thank you. Very nice talk, I think.
Okay, maybe I can ask a, okay, so there was a question, like Bruce, go ahead.
Yeah, so that was very nice talk. I'm almost embarrassed to have a question for you. But when you talked about the regime of phase coexistence, actually it's on this slide, I guess, in the hashed green area. And I was just curious if you could clarify what is meant in what exactly coexists in this area, because as I understood it, you had a spectral function which evolved as you went from the more insulating side towards the critical point, until you got these two distributions as a function of frequency, which touched, and on the metallic side. Oh, sorry. Yeah, it's the other way around, right? So exactly. So you have an evolution of the spectral function from the metal to the critical point for the insulator, and then so within this coexistence region, then the spectral function would be a coexistence between what the two panels that are shown at the bottom on the right. Is that the way to think of it? Or I'm just wondering how to think about the coexistence.
No, that's a good question. I was too brief at this point. So let me just explain this in better detail. So this coexistence regime is a true thermodynamic coexistence, like with any first order transition, which means there is a stable insulating phase and a stable metallic phase. What I'm showing here in red, so one can understand the spectral functions by essentially looking at the evolution of the two blue spectral functions, which are shown on the left and right. So let me just explain this. The insulator, again, starts out with these two well-separated Hubbard bands. And then as you move towards the left, the Hubbard bands come closer to each other. And then at the end of this coexistence region, this is where this red arrow points to, you get the two Hubbard bands which just touch. So this is the spectral function of the insulator, of this insulating phase, which again in this regime is actually only metastable. Independent of this, there is a metallic phase, which starts out with this blue spectral function on the left. And then as you move towards the right on the phase diagram, this quasi-particle peak in the middle gets less and less weight. So in other words, it becomes narrower and narrower. And this is essentially saying that the metallicity becomes weaker and weaker in a sense, until you go to this point here. I hope you can see my mouse. This is the other side of the coexistence regime. This is UC2. And at this point, actually, the middle peak disappears. And so it disappears in a way that the quasi-particle, the weight of this quasi-particle thing continuously goes to 0. Which means if I'm here in the middle of the coexistence regime, there are really two phases, and you can actually see this in experiments also as two domains of an actual sample. And one phase is metallic, and this has a quasi-particle peak in the middle. And the other phase is insulating, and this has no quasi-particle peak in the middle and really has zeros or very small spectral weight at the Fermi level. And again, in actual experiments, this you can very nicely see in these organic Mott insulators, which can be tuned by pressure. There is this coexistence regime, and you can see domains which you can even image by STM techniques. And you see insulating and metallic domains.
Okay. Oh, yeah. Okay. Very good. So it is a true coexistence. Yeah. Okay.
Yes.
I understand. Good. Yeah. Thank you.
I have a quick question. Oh, sorry, Young Beck, go ahead. I was.
Oh no, it's just a related question. So, so when this upper and lower Hubbard band touches there, they supposed to give you this critical behavior. So, what happens to that metallic solution at that point? Then there's no signature whatsoever for this quasi-particle peak.
That's true. So again, this, as I just explained, this here is a coexistence regime, and as with thermodynamic first-order coexistence, the two phases don't know anything about each other. Which means if you take the blue solution and go through this first green line, it doesn't notice anything, right? This is like with any first order coexistence. So if you, let's say, if you have liquid gas and then you have a coexistence regime, but you take the phase which is stable through the line where the metastable phase disappears, the stable phase doesn't notice this, which means the blue solution here sees nothing. And this is why the story I told you has gone unnoticed despite 30 years of DMFT research. Because if you just look at the thermodynamically stable phase, you just follow this blue curve up to UC2 and you don't see any of the physics which I described. You have to decide to study the metastable insulator to see this physics.
So then why the sort of transport signatures doesn't know anything about this blue metallic solution at all?
Oh, sorry. Okay, I was half cheating to you, and I should have emphasized this. Let me just get back to the relevant slide. So first, let me emphasize the curves, the puzzle findings which I advertised here only show data above TC. This is Doposavljevich's paper, only data above TC. This is Kanoda's paper, only data above TC. So no problem here. What I showed to you is somewhat different. I showed to you this plot, which was a scaling plot. And actually this branch of the curve here also, sorry, this branch of the curve, which goes very deep in the insulating state, actually goes to temperatures below TC. And what we decided is to follow the metastable solution. And this plot here as well is generated by focusing on the metastable solution in this regime. So in other words, if you focus on the thermodynamically stable thing, then everything what I told you is cut off at this big blue line where the first order transition is.
Okay, I see.
But decided to focus on the metastable solution in order to make the argument that the physics of this metastable solution drives the criticality. And so in an experiment, you wouldn't see the physics below this blue line unless you're able to stable the metastable stable state, which in numerics we can. But if you just focus on the stable solution, all this physics is cut off at the blue line.
I see.
If I can ask a question, if you go back to the plot you were showing to Young-Beck at the beginning.
The spectral function plot?
Yeah. With the phase diagram, yeah. So yeah, I find it very nice that you are able to identify the critical point as the coming from the red spectrum. In the first papers of Borslavljevic and Terlecka, they were not clear where the transition was, right? I mean, where the QCP was. So I think it's nice that you were able to do this, and it sort of convinces me. But I have a question nevertheless, which is that if you look at the red line that starts from the critical point and separates the two thermodynamic phases, when you go all the way to zero temperature, there's supposed to be a critical point there as well.
You mean this one there?
Yeah.
So you mean UC2 at t equals 0?
UC2 at t equals 0, at least in the some of the early papers. I don't know if it has changed, but they were saying that the first order transition goes to a second order transition at t equals 0. So you sort of have two possible critical points.
That's a relevant remark, which, however, does not change the discussion. So let me explain what happens at UC2. I guess I mentioned this very quickly a few minutes back. So at UC2, you take this metallic solution, the blue spectrum here on the left, and upon approaching UC2, this quasi-particle weight becomes smaller and smaller. And what makes people call this second order is the fact that the quasi-particle weight vanishes continuously upon approaching this point. So in other words, here the quasi-particle weight is finite, and then there it goes continuously to 0. However, this does not open the possibility to have critical behavior in the sense of frequency power laws, right? Because at the point, the weight of this peak has just gone to 0, and you are left with a spectrum which consists of two preformed Hubbard bands and nothing in the middle.
Mm-hmm.
In other words, we also looked at this spectrum in detail, but that's in fact well documented in the literature. So there's no possibility to have criticality in the sense I discussed here.
Okay, thank you very much.
Which also means you can look at finite temperatures above this point, and it's entirely boring.
Yeah. Okay. Thank you.
Okay.
There
was a question in the chat box from Andrew McFarlane. I don't know if Andrew, you want to ask it, or you're muted right now.
Hi, Matthias. Thanks for the nice talk. I'm actually in another meeting at this moment. I was just interested in this coexistence region. If it's really non-equilibrium, one expects some time dependence and equilibration towards the real thermodynamic phase, which is the metal in this case. Why is that not fast? Like, what is preventing it from equilibrating?
You are asking a very interesting question, which I didn't touch upon at all. So all the statements which I made concerning the physics below this orange line were statements about the metastable solution found in dynamical mean field theory. Mm-hmm. And it's a technical statement that we are able to stabilize this on the computer, and it is not a statement about physics. Mm-hmm. However, again, if you look at experiments in this regime, then you see domains. Yeah. Which means in principle, it's clear that the two things are metastable. Now you ask, you could ask what's dynamics in this regime? What determines the amount of hysteresis you get there? And I'm not sure whether I can effectively answer this. So
is the lattice involved intrinsically, like in the experiments? Can you?
Well, you have to. So the answer is certainly yes. You have to keep in mind that the true system also has long-range Coulomb interaction. which means the screening properties are different in the metal and the insulator. And I would think that this at the end stabilizes domain formation. So I mean, I'm not sure whether this has been carefully studied, so I'm guessing at this point. But I would imagine that in a system with purely short-range interaction, the domains would be less stable in an actual experiment compared to a system which has Coulomb interactions. But again, that's a guess.
Okay, thank you.
Any other question? I don't see any. Okay, so if not, we can stop here, and maybe we can all show our faces on the video. I'll stop recording after. And Matthias, I don't know if you're available. I realize it's late now in Germany, but André-Marie and I wanted to maybe chat with you if you can stay for a few minutes behind.
We can certainly do that.
That would be awesome. Thank you. Okay, so thank you very much. That was an excellent talk. And
I apologize for the technical problems.
Thank you.
oh, yeah, well, it happens. Okay, thank you very much.
Okay, so I